In this episode, we're going to zoom in on what happens on a local network when one device needs to send traffic to another device, because this is where a lot of hidden trust lives. Beginners often imagine that if you know an IP address, you can just send traffic to it. But on a local network segment, the system still has to figure out which physical or link layer address corresponds to that IP address, so it can actually deliver frames on the local medium. That mapping step is handled by Address Resolution Protocol, ARP, in IPv4 environments and by Neighbor Discovery Protocol, NDP, in IPv6 environments. These mechanisms are essential for basic communication, but they can also be exploited because they are built on assumptions of local trust and cooperative behavior. When attackers can manipulate these mechanisms, they can redirect traffic, intercept communications, or disrupt connectivity, all without breaking encryption or guessing passwords. The goal here is to make ARP and Neighbor Discovery feel like understandable systems with clear risks, rather than like obscure trivia. Start with the core problem both ARP and NDP solve. A device knows a destination IP address, but it needs the destination link layer address to deliver a frame on the local network. Link layer delivery uses addresses that are meaningful on the local segment, and those addresses are different from IP addresses. So a device needs a way to ask the local network, who has this IP address, and what is your link layer address? ARP solves this in IPv4 by using broadcast queries on the local network. A device sends an ARP request asking for the link layer address associated with a particular IP address, and the device that owns that IP address responds with its link layer address. The original device then stores that mapping in a cache so it does not have to ask repeatedly. This is efficient, but the cache introduces an opportunity for poisoning, where false information is inserted and then trusted. The key beginner insight is that local delivery depends on these mappings, and if the mappings are wrong, traffic goes to the wrong place. Neighbor discovery in IPv6 environments is a broader set of functions, but at a beginner level you can think of it as the IPv6 way to discover neighbors, resolve link layer addresses, and maintain local network information. NDP uses messages built on Internet Control Message Protocol, ICMP, for IPv6, and it includes mechanisms for address resolution similar in purpose to ARP. NDP also plays a role in other local network tasks, like discovering routers and ensuring that addresses are not duplicated. The details can get deep, but you do not need to become a protocol engineer to understand the security point. In both ARP and NDP, devices accept certain kinds of local network messages as truth, and that acceptance can be abused by an attacker on the same local segment. Local network access is therefore a meaningful security boundary. If an attacker gains local presence, they can often attack the trust mechanisms that keep local communication working. ARP works through a simple request and reply pattern, and understanding the pattern makes spoofing risks easier to see. When a device needs to send traffic to an IP address on the local subnet, it checks its ARP cache. If it has a mapping from that IP address to a link layer address, it uses it. If it does not, it broadcasts an ARP request, essentially asking the local segment for the owner of that IP address. The owner replies, and the sender updates its cache. The weakness is that the system typically trusts the first plausible reply it receives and trusts future ARP messages that update its cache, because ARP was designed for cooperative environments. An attacker can exploit this by sending forged ARP replies that claim an IP address is associated with the attacker's link layer address. If the victim accepts that mapping, the victim will send traffic intended for the real destination to the attacker instead. This is called ARP spoofing or ARP poisoning, and it turns a local attacker into a traffic redirection point. The real danger of ARP spoofing is not only that traffic can be diverted, but that it can be diverted in ways that are hard for victims to notice. If the attacker simply drops traffic, it becomes a denial of service, and users might notice quickly because things stop working. More subtle attacks forward the traffic after intercepting it, creating a man-in-the-middle position where communication still works but is being observed or manipulated. Even when encryption protects content, a man-in-the-middle can still cause disruptions, perform downgrade attempts in some contexts, or collect metadata about who is communicating with whom and when. If some traffic is unencrypted, The attacker may be able to read credentials, capture sensitive data, or alter messages. A key beginner misconception is that these attacks require controlling routers or breaking into servers. In reality, if an attacker can join the local network, they can exploit local trust mechanisms to position themselves between devices. That is why protecting local network access, such as controlling who can connect to a network and segmenting untrusted devices, matters so much. Neighbor discovery spoofing risks are similar in spirit, because the underlying issue is that local discovery messages can be forged or manipulated. In NDP, devices use messages to discover link layer addresses and to learn about routers. If an attacker can send malicious neighbor discovery messages, they may be able to mislead devices about where to send traffic or who the router is. That can enable traffic redirection or denial of service. NDP also includes mechanisms like address duplication checks, and attackers can exploit these to create disruption by making it seem like addresses are conflicting. Again, the details of every message type are less important than the trust model. The trust model is that devices accept certain local network announcements as valid. When that trust is abused, local traffic can be rerouted or broken. Beginners should recognize that IPv6 does not magically eliminate local spoofing threats. It changes the mechanisms, adds features, and can improve certain aspects, but local trust problems remain if protections are not in place. A crucial concept in both ARP and neighbor discovery is caching, because caches are where false information becomes persistent. A cache exists for performance, because repeatedly asking for link layer addresses would be inefficient and noisy. Once a device learns a mapping, it keeps it for a while, and it may update it when it sees new information. Attackers target this by injecting bad mappings that persist long enough to be useful. The longer the cache lifetime and the more easily it is updated, the easier poisoning becomes. The security lesson is that many attacks are not about breaking cryptography, but about corrupting the data that systems rely on to function. If a system relies on cached trust without validation, an attacker can corrupt that trust. This idea shows up across cybersecurity, not just in ARP and NDP. It is the same pattern you will later see in name resolution poisoning and in credential token theft. Understanding ARP poisoning helps you recognize a general class of attacks based on manipulating trusted caches. Local trust also matters because many environments implicitly treat the local network as safer than external networks, which can lead to weaker controls internally. For example, some services may be exposed only internally because they are assumed to be protected by being inside the network boundary. If an attacker gains local access, those internal services become reachable. ARP and neighbor discovery attacks can then be used to intercept internal credentials or to redirect internal traffic. This is why segmentation and the idea of not trusting internal networks blindly have become more important. A local network should not be treated as automatically trustworthy, especially in environments with guest access, unmanaged devices, wireless networks, or many endpoints. When you reduce local trust assumptions, you reduce the value an attacker gains from simply joining a segment. That is also why modern security models emphasize identity and device trust rather than location alone. ARP and NDP remind us that physical or local proximity can create powerful opportunities for attackers. Detection of local spoofing is challenging for beginners to conceptualize, but the basic idea is to look for inconsistent mappings or unusual changes. If the mapping for a critical IP address suddenly changes to a different link layer address, that can be suspicious. If many devices suddenly claim ownership of an address, that is suspicious. If the default gateway's mapping changes unexpectedly, that is especially dangerous because it can redirect large volumes of traffic. Even without discussing specific tools, you can understand that monitoring for these patterns can help detect attacks. Prevention strategies in concept include limiting who can join the local network, segmenting devices so untrusted devices cannot share a segment with sensitive systems, and using network features that validate or restrict address resolution messages. The specific mechanisms differ by environment, but the principles are stable. Reduce attacker ability to participate on the segment, reduce the trust placed in unauthenticated local announcements, and increase visibility into changes that should be rare. Those principles apply regardless of whether you use ARP or neighbor discovery. From an exam perspective, ARP and NDP questions often test your understanding that these protocols map network layer addresses to link layer addresses on a local network and that spoofing can redirect traffic. If a scenario describes a user being redirected to an attacker's system on the same network or traffic being intercepted on a local segment, ARP poisoning is a likely explanation in IPv4 settings. If a scenario describes IPv6 neighbor messages being abused to redirect traffic or impersonate a router, neighbor discovery manipulation is a likely explanation. Another common exam pattern is asking what type of attack enables man-in-the-middle on a local network without compromising the router itself. That is where ARP spoofing is a classic answer. The key is to recognize the threat model. Attacker has local network access and is exploiting trust in address resolution. When you see that, you can connect the dots quickly. By the end of this episode, you should be able to explain that ARP and neighbor discovery exist to make local delivery possible by mapping IP addresses to link layer addresses, and that these mechanisms carry local trust assumptions that can be abused. ARP uses requests and replies and relies on caching, which can be poisoned by attackers to redirect traffic. Neighbor discovery provides similar functions in IPv6 environments and can also be manipulated if local messages are not protected. The security risk is not only denial of service, but also man-in-the-middle positioning, where an attacker quietly inserts themselves into traffic flows. Understanding these protocols builds your ability to reason about local network threats and helps you see why network segmentation, strong device access controls, and visibility into local mapping changes matter. When you can explain where traffic goes and how local address resolution determines the path, you have a stronger foundation for the next topic, which is how name resolution and DNS trust can be attacked in similar cache manipulation ways.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.